discuss introduction to classification and specifically the KNearest Neighbors classifying model. Up until this point, we've been doing purely regression-based stuff, whether it's linear regression or lasso or ridge regression. It's all been fitting models that try to minimize the amount of error our data has when we plot points versus another, whether that is fitting a linear straight line or a line that can curve a bit. The name of the game has been minimize the errors between those points and the line itself. Classification deals with a different type of problem. So today we'll discuss what classification is. We'll do an introduction to KNearest Neighbors specifically. We'll talk about one example and potentially a few other applications. For context, KNearest Neighbors is probably one of the top 10 most used classification models, and we'll figure out why that is. And then we'll do a coding implementation. And based on what you guys said, we'll shift a bit more time to be focused on walking through exactly line by line code stuff and a bit less on slides. So first and foremost, can you guys guess what classification is? Make a guess. It's part of the name, otherwise I wouldn't ask.
Just throw this out there.
Yes.
It's a way to group group data by two or more groups. Guessing something to do with machine learning, where at least with supervised learning, once we have something, we want to classify our testing set into something that's relevant to us. That might be too specific, but that's
yeah, no, you're exactly on the right track. Something about groups and something about supervised machine learning. Any other type of things that you think you did not touch on that you think classification could encompass? Or rather a distinction between what classification may be used for and what regression has been used for, the holy grail? What's the difference between like groups and say what linear regression is doing? Yeah.
I feel like when we're talking about classification, we're kind of describing rather than predicting. Whereas with regression, yes, it's if we don't know if there's cause and effect, where it's still correlation, but we're trying to get towards describing a relation.
Yeah, so we still will be making predictions, but you're touching on the right things. Classification deals with predicting non-numeric features. So exactly what you said, grouping things together is a type of classification. The idea that it couldn't be predictive, however, is not necessarily true because you could still try to be predicting what group something belongs to. Regression, on the other hand, deals with predicting continuous values. So, home prices, as opposed to perhaps what neighborhood a home is in. So
we can still use categorical variables in regression.
You can, but the output is what we're concerned with here. So what we're predicting, whether that prediction is a group or a class, right, versus a numeric value. So if you think about all types of regression, you're always predicting some numeric outcome. Now it gets tricky, the lines get blurred at points because there are some regression models where you're still using it to predict groups. In fact, that's what you'll discuss with linear or logistic regression. But nonetheless, the general difference is classification deals with assigning things to groups and determining what features imply that this object goes in this group. Whereas regression is like, here's a bunch of inputs, whether those inputs are groups themselves that you've encoded as variables, and says, here's a numeric value that I think you would get based on that group, those inputs. So example one, if you have a home with X bedrooms, that is Y square feet, and Z lot size, what's the price of the home? What type of problem is that? It's a regression problem. And why? What if I had groups? What if I had Republicans, Democrats, and Independents? It's still a spectrum.
Those are specific points that we're choosing.
Yeah, there's a distinct cutoff between party identification, whereas the dollar value between 5 million and 5 million and $1 is not a new group. So therein lies the continuous versus grouping strict cutoff. So the second example, I have an unknown fruit that's 5.5 inches long, 2 inches in diameter, and yellow. What type of fruit is that? Is a what type of problem? Yeah, classification, right? So maybe you picked up on this now, maybe you didn't. This was a pun. Class guesses. Okay. So I stole this from the scikit-learn documentation, but it's a cheat sheet for what type of algorithm you want to use to describe a problem. And of course, we haven't discussed dimensionality reduction or clustering, so you can ignore the bottom two. But of course, this will be a useful reference later for those exact reasons. But I like the way it walks through, and basically, the huge delineation is this point here, which if you can't read it in the back, you start with, what are you trying to predict? How many samples do you have? And then you go, are you predicting a category or not? And if you're predicting a category, then it's likely that you're doing something with classification rather than with regression. So here I'm going to do a brief dip into logistic regression for a second, just because you're going to be talking about it, I think tomorrow or Wednesday, one of the two. And it plays into this quite a bit. So logistic regression is a regression tactic where the output is 0 or 1. So, and some value in between those two, but it's bound by 0 and 1. So data scientists may use a logistic regression to describe a categorical problem. For example, is this person a Democrat or a Republican? I will say Republican is 1, Democrat is 0, right? That is what I'm talking about with the line getting blurred. The difference is with a logistic regression, you're still going to get an output that is a continuous value between 0 and 1. And you're going to say if that value exceeds 0.5, oh, then we're going to say it's 1. And if it's below 0.5, we're going to say it's 0. Therefore, logistic regression is still a regression tactic that is often used, almost exclusively used, for classification problems. It's still a regression problem because we're still getting a continuous value, 0 to 1. But it's used to then be like, all right, the strict cutoff is 0.5. So that's what I'm talking about, where like the line can get blurred. But the type of problem you have in front of you is determined by what outcome you're seeking, whether that outcome is class-based or continuous value-based. Does that make sense? That's cool. So there's many different types of classification algorithms that we can use. And I found this really cool code that someone wrote for the scikit-learn documentation that I added to the repo. So let's hop on over to the code that I put in the repo for a second, just to run it. And this was the guy that wrote it, not me, Dale Verkelrux and Andres Miller. Basically, if you run the first approximately 100 lines, 105 lines of that document, we're not going to run through that because it's just literally plotting what each different classification problem looks like, and then it outputs a bunch of plots. So I'm just going to show you what the outcome of that is, what the plots that it generates look like. And I provided the code so you can generate these plots yourselves and look at it closer. So the left-hand column is going to be the data set that it generated. And then every column after that is going to be how different classification algorithms would have classified those data points, right? So this first quadrant, first row. If we use an algorithm called the KNearest Neighbors classification, you'd end up with points like this. Linear, SVM, I think we'll discuss like week 8, decision trees, RBF SVM, random forests, and so on. Don't be too concerned with what each of these are, so much as, because we'll discuss them in depth, so much as the clear ways in which they hash out the data points given. So something that I want to be a key takeaway simply from showing you all these methods is sometimes these methods are quite accurate in some instances. So if we look at linear SVM for this data set, it actually looks pretty poorly at describing this data set because they're overlapping within the same bands, if you will. Sometimes it's quite accurate. So if you look at decision trees for, or rather, actually KNearest Neighbors does a great job with this last one. KNearest Neighbors does a great job at classifying this set of points like this. Without knowing what each of those things are doing or like how they got to those conclusions, the takeaway of this graphic is the type of classifier you choose is perhaps obviously very dependent on the data that is in front of you. So this connects back to all the discussions we've been having about choosing which model to work with initially. And if you think about it and you think, oh, well, I mean, we've only worked with like linear regression, there's really not that many models to choose from. Here we've plotted 7 different classifier models, and you can see why some of the tactics we've discussed, for example, make your estimate incredibly biased to choose your model before tuning that model, would get you to a conclusion of, man, which category of model do I want to use in the first place? So today we'll be discussing the first of these, the KNearest Neighbors, because it's pretty intuitive, highly accessible, and just a great introduction to classification problems. Okay, so what is KNearest Neighbors? KNearest Neighbors is a non-parametric, lazy learning algorithm that predicts outcomes based on the similarity of the input features and how those input features match up to our training set. So let's like break that down. That's a lot. Non-parametric. Non-parametric means it does not make assumptions about how the data is plotted or of what scatter plots may prescribe about our data. And that will make more sense once we do some visual stuff. Lazy. It's lazy, KNearest Neighbors is lazy because there's not a lot of tuning we need to do or a lot of work and pruning. I mean, obviously you have to make your data so it fits within the data set first. But once you're there, you don't have to do much with the model itself to make it fit your data set. Sometimes in some classifiers, you need to splice up your training set in specific ways or tell it to only work with some of the data. KNearest uses often all of your data to prescribe classes and then prescribe out of sample data points based on what it's learned from those classes. The third thing, it's based on feature similarity. So this is why KNearest Neighbors is quite powerful, and for the same reason where the drawbacks come from, frankly. So you can think of KNearest Neighbors as a spatially dependent way of classifying things. So here's where we're going to introduce like our first example, which will hopefully clarify a lot of this jump. Let's go to the Republican and Democrat example, because the link here, or it's not the link that we'll go to in a moment, will be using the same example. Republican and Democrat classification, right? Those are 2 classes. Depends on perhaps how someone feels about a list of issues. And then how an individual feels about those list of issues may actually, so some features may be highly descriptive of how someone feels, for example, like church attendance, or for example, how they feel about taxes, we'll say. Church attendance and taxes are what we'll go on. For a regression is going to take each of those features and ascribe coefficients to those features. And then based on the input that you give it, it's going to output, of course, relatively where you think. Whereas KNearest Neighbors says, hey, maybe each of these things that we're trying to classify exist in groups and clusters of one another. So perhaps these points don't exist in isolation. Like, I have this person that attends church this much and thinks this about taxes, goes this direction. Instead, think about it like, I'm an individual who thinks taxes should be, say, very low and goes to church 7 times a week. If you put another individual next to me, or rather another individual who has the same types of beliefs close to me, we're likely to be the same type of classification. The difference between what that just did and what regression would do is regression wouldn't have considered where me and that other person, how close we are, so to speak, in our features. So this will become abundantly clear looking at this. Okay, here's an example of Republican Democrat classification based on KNearest Neighbors. KNearest Neighbors says, here's this point with this set of features, and here's another point with this set of features, and how close that other point is to the point that's already in our training set. So an example of me, 7 days a week church, low taxes. Someone else comes and they're also 7 days a week church, low taxes. We're going to be plotted close to each other. KNearest Neighbor says how that person, based on those features, falls into Republican Democrat is likely dependent on how close that point, that new person in our data set, is to me. And in effect, we can actually make each out of sample or new predictive point ask the same question about how many people we have in our first data set. So think about an example where we only have 2 people. That's it. We only have 2 people, and we only know how they feel about a list of issues. Taking someone and putting them into our data set close to those 2 people, it's going to be nearly a coin flip on how close that person is to 2, say, disparate issues. However, if we have a data set of 100 people, and we therefore have, these 9 issues this way, 1 issue this way, these 8 issues this way, we kind of have kind of a spectrum in some sense to think about it, of how a bunch of people feel about the list of 10 issues. Once we bring someone else into that fray, so imagine 100 people standing in a room, and they all have different issues in the same 10, different stances of the same 10 issues. We bring someone into that conference room who has never been there before and has views closest to someone in that grid of 100 people, where that person answered their survey on the 10 issues and ended up standing next to the conference room of 100 people is what we are going to say that person's identification is. If you think about the conference room and it only had 2 people in it, that's going to be substantially less accurate than if it had 100 people. And that's especially the case when we're grouping based on prior examples. So this plot here is an example of data that has been randomly generated, or rather, it was generated around this line here, and then there was added stochastic noise. So it was perfect, like red, blue, and then randomly added a bunch of different red, blue on the other sides of the line. And this is an example of how KNearest Neighbors would work to classify these points. And notably, our K value for this one is 1. That means if I'm in that conference room with 100 people and someone walks in, where I put them, I'm only going to ask or be relative to the first nearest person to each of them. I'm not going to go ask this person and then 1 degree of separation away and then another degree of separation away. I'm only gonna ask 1 degree of separation away. And then that's where I'm gonna assign that person in the conference room for where they stand on a list of issues. How that would apply to here is this, any given hexagon here. This one, which has been described to be or Democrat, blue. Any out of sample data point that comes in here is most definitely going to be classified as Democrat. 1 away every single time is a Democrat. Now, the stochastic noise that exists here, this is our data set. So these people are true Republicans that have fallen on this part of our spectrum. But we can see how if we put a new hexagon in this space where it would fall, in the graphic right above it, hopefully it's not too faded, we can see. So like, for example, if any person came into this space, we're gonna say blue. If any person came into this space, we're gonna say red, and so on and so forth, based on how close they came relative to the, say, neighborhood of these given points. So now I'm going to tune this model a bit, and I think it will become abundantly clear about what K-nearest neighbors is doing based on the distance of one point to another. I'm going to increase the value of K, which is going to say take into account more points around you rather than the closest one to you. In effect, we're saying no longer care about your neighbor, your one neighbor, but ask the person next to him as well, and so on, and next to him, and next to him. And you can imagine if you're standing in a line of people and you felt this way about 10 issues, and you ask the person next to you, and they're like Democrat, next to you, Democrat, next to you, Democrat, you're probably pretty safely on the Democratic side of the room. However, if it was like Democrat, Republican, there's a bit more uncertainty. And how we account for that uncertainty depends on how many neighbors we have. So this interactive is posted under resources in the lesson that I posted. And you can see here's K equals 11, where it's taking into account the 11 closest points. Note how the bottom left-hand corner, those red, completely become blue. We can keep tuning it all the way until K equals n, the number of data points. Every point is taking into account every other point in our data set. It looks like this, where the lighter in gradient it is, the less certain it is about a classification. So this is where you can see there's a clear trade-off in how specific or considerate we are of data points already in our training set versus being more aloof, I suppose, to points that could come into our data set. So you got to think there's some ideal value between these two, right? There's probably some ideal value where RK minimizes our classification error, where we feel like when we have someone walk into that room of 100 people in the conference room, and let's say we know their true party identification, but all they can do is ask about the 10 issues and find out where they fit in that room. Minimizing the error, being certain about what we should classify them as, depends on how many neighbors we should have them care about in the first place. So for example, if we had that person taking into account every other person in the conference room, we likely wouldn't be able to be very certain about where we would classify them. And that's not a very good model. However, if we had to only care about the one person next to them, perhaps we're not taking into account enough of our training points, and therefore our estimate varies too much. either it cares a lot about all of our data points and is very biased about those 100 people already in the conference room, or it's not very biased, and that one individual that comes in the conference room could have ended up in perhaps a few different points.
With larger sample size, does that kind of decrease the effect of like going up like 1K?
When you mean decrease the effect, do you mean?
Like, so like the really big, like big jump in size going from like 5 to 6 on this table. People, the data set are a lot larger. Would that be less dramatic?
Not necessarily, actually. Once you have a data set that is sufficiently large above scikit-learn documentation claims 50, but even that's a little low. It's going to be the same as any other case where the more points you have to train on, generally just a bit more certain we can be. And so what you're getting at is the uncertainty error. And if you think about it, the more people we can survey about those list of 10 issues, the more certain we can be about how out of sample survey answers fall into Republican or Democrat. Does that answer your question? Yeah, I think you had a question earlier.
I was wondering where that line came from. Is that generated from data? Or?
That was, so the way this graphic was constructed was, there was just everything on, has nothing to do with KNearest Neighbors.
Okay.
Nothing. This line, everything above it was going to be red, everything below it was going to be blue, and then stochastic noise was added so that it's not perfectly already good to go. KNearest Neighbors is solely the practice of identifying which way someone would go on. So in an ideal world, everything would be red, everything would be blue, and we would be hunky-dory. But we have some stochastic noise because to show the value of increase in our K, we can see how we can correct this error.
But that noise is from the data. It's not just randomly thrown in.
Well, both of those things. It's from the data, but this data isn't real data.
Okay.
Yeah. Yeah, but that noise is from the data,
Okay.
which was randomly generated. So I encourage you all to right now play around and try to find what value of K you think is best for this data, knowing that everything north of this line should be red, everything south of it should be blue, but you still want to be as certain as possible in your estimates. That is to say, you don't want to just do K as 100. I'll give you 5 minutes to do that. Did everyone find the link? Yeah. What do you think? 3? Here's 3.
Mine is different.
Oh, you probably down here. They will all be a bit different, but we'll arrive at the same conclusion, I promise. Well, which is not what you think, unfortunately. But you said 3? What else did people say? So here's my data at 1, which is different than your data. 6. Okay, here's what 6 looks like. What are some advantages, disadvantages about this one?
Less error, but also less certainty. Like there's less red ones in the blue area and blue ones in the red area.
Yeah.
But there's also white spaces, so there's no room to do that.
Yeah, you guys are interpreting it right. That's sweet. Someone I think said 11. What do we think about this value of k? Here's 11. Here's 6. Do we have any other values? 10. Yeah.
As a question, is it like you're going to evaluate this model? Does it matter like how blue it is, or does it matter that?
Good question. It doesn't necessarily matter how blue it is, but in determining how light or dark our shade of blue is, we're affecting at the margins or other points, right? So for a given point that's already shaded a bit blue, we're good. But in effect, by getting to a stage where we have some that are lighter shades of blue, the ones that are at the margins, the marginals. So I mean, if you take this to the extreme, lots are shaded lightly blue. And that's not a good model because it leads to, at the margins, a lot of uncertainty. So for one given point, the answer is no, but K-nearest points aren't in a vacuum. In fact, that's exactly what the antithesis of K-nearest neighbors is. Points are, in fact, relative to one another. So one light shade of blue, not so bad, but what that does for other points is the ones at the margins may be even less certain. Okay, so I mean, we arrived at like a range between 6 and 11. And the truth is, the answer for this, we can't conclude without doing a bit of our own code to determine what values we would want to have, which is kind of annoying, right? But the value of that exercise is that we saw in practice the bias variance trade-off. So if I dial this up, what's the difference between 6 and 11? Or take it to the extreme, 1 and 100. What's the difference? In the context of bias and variance.
As you get higher, is it less bias and more variance?
Which way is it?
I'd say that's okay.
Which is it? Debate it out.
K equals 1 is over a bit, so it has very high variance.
Okay, she argues k equals 1 is overfit, and therefore there's high bias, low variance. I think you said the opposite.
Yeah.
Okay, what?
It just looks like there's a lot. Now I'm questioning it now that I think about it.
Didn't we say variance goes up as complexity goes up? So
Yes.
wouldn't having a higher K value make complexity go up?
Yes.
And wouldn't that make variance go up?
Yes.
So more variance error as you get higher up,
Yes.
and less bias error. But, so if you're at 1, it's a lot of bias error. He wants a variance.
So let's go down to our graphic.
Readiness.
Error-due bias decreases as we get more complex, because think about it. What you were looking at is you're like, these points are very conclusively red and blue, and therefore we have a biased estimator. In fact,
And we would do it perfectly there, testing, or our training.
not necessarily actually. So here, let me do this, and then I'll get back to that. So if we have a model that only cares about the single nearest point, it's not taking into account, of course, 2 and beyond. And therefore, and actually take a step back, 2 and beyond of what? Of our training data. It's only taking into account the one nearest point in our training data. If we increase that value to 2, it's taking into account the 2 nearest points in our training data. 3, the 3 nearest points in our training data, all the way up until k equals n, all the points in our training data. What in fact that is doing is it is making our model more and more representative of the training data rather than the out of sample data. What you were seeing with the colors getting lighter was how it predicts out of sample points. So as we increase complexity, error-due bias goes down. Remember the line of linear fit versus like a polynomial 8, touching every point versus only some of them, maybe none even. Nonetheless, variance increases as our model gets, as we decrease bias error, because think about it in the context of k-nearest neighbors. If you take into account the 100 nearest points, it's going to be less conclusive, and the model could fluctuate more about where out of sample points could go. So that's why explaining the bias variance trade-off in the context of something like k-nearest neighbors, I think is more illustrative, because you have a very explicit tuning parameter. Like your complexity is literally a number that is equal to k, whereas in linear regression, it's a number that's equal to the degree. And it's kind of like silly why you would choose a degree extremely high. Here, it's like, well, there's actually an argument to be made for degrees, complexities that are pretty high. And it makes it very clear the trade-off you're making in terms of basing things on your training data versus being sensitive to things that could come in your out of sample data. Is that satisfactory? Okay. Yeah, think about it in terms of it's relative to your training set. Relative to your training set. So how biased our estimates are by the training set versus out of sample points. All relative to the training set. Okay. Actually, before we do an example, do you feel like you have a grasp of k-nearest? So it's non-parametric, cares about points near points in our data set, where near is defined as the features. So in the example of Republican Democrat, the features are how they responded to those 10 survey questions. How closely someone answered those 10 same survey questions explains where we're going to classify them as. Right? People seem a little bit uneasy, so if you have questions, just ask. Okay. So let's think about an application. And this is the one we're doing code. A botanist has a meadow of a ton of flowers. And he does not have time to survey all the flowers in that meadow. He also doesn't have the budget to buy research assistants to do it for him. So he wants to find a quick way where if he gets a sample from that meadow, know what that flower was, or is rather. Can we see why this is a classification problem? Why is that? What's the key giveaway?
For that type of flower.
Yeah, it's looking for a category. You're either in column A, column B, or column C. There's not much ambiguity between them. End up in one of those columns. So we'll use the KNearest Neighbors classification to explain this problem, where we have sepal length, stem length, and leaf length. And based on what we plot in our data, what we already have in our training set of the sepal length, stem, petal length, maybe color, whatever an out of sample point comes in and looks like, how closely it resembles the length of the stem, as well as the leaf, as well as the color, is what we will say that flower should be, based on our training set. Right? So like if we plotted the neighborhoods, if you will, of the stem, color, sepal length, when we pick a flower out of that meadow, bring it in, and say, well, I mean, the stem is not exactly between 8 and 10, but the color matches spot on, and the sepal length is also roughly within the range of this one type of flower, therefore it is this one type of flower, is the KNearest Neighbors application. Right? So strict categories where we are biasing or determining our estimates based on feature interactions already in our training set. So let's talk about some benefits and drawbacks of KNearest Neighbors. The first benefit is that it's pretty easy to comprehend, right? You just have a bunch of points. How close out of sample points are to the features in our sample points is what we say the grouping is. Second advantage is model training is super fast because it uses basically all of our data set and plots those 100 survey people, right? Plots those 100 people that filled out those Republican and Democrat surveys. And then just assigns what out of sample points based on those survey answers. And then of course, can be used for classification just as much regression. And we won't delve into the regression bit too much at this stage in the game, but it's a great classification model. So the drawbacks are by token of requiring all of the training data, or you could of course take out some of the training data, but whatever you've trained on is going to be all of your training data. And that's a drawback because it requires a large amount of training data, which is also computationally expensive. Imagine if your training data continues to grow, what amounts of your training data do you take out to make it so your model continues to run just as fast? You can see the trade-off pretty clearly. And that's feeds into point 2. Prediction phase is slow when n is large, when you have a lot of training. So for example, one of the problems that we have is classifying letters and text data. And in an ideal world, we're classifying what the letter is about. And in an ideal world, we would be able to take into account every single letter that's ever been sent ever before and what categories those letters received, and then match a new letter against those categories. However, with text data and with literally thousands of letters coming in weekly, it's incredibly computationally expensive to take into account every single training point. And then you say, well, you can prune the model, and you can, but if you're pruning the model, you maybe should have just chosen a different model in the first place. So that's what we did, right? The other thing is that it's sensitive to irrelevant features because it's taking into account every single feature when you classify something, right? It's taking into account the sepal length, the petal length, and the color. It's taking into account those 3 things. Even if you chose features that you thought made most sense for your model, so you're like, oh, well, I just wouldn't choose irrelevant features. Well, that's data science, right? We don't know what is and is irrelevant. So even if you choose ones that intuitively make the most sense, they may not all make the most sense in truth for predicting your data, and by margin of no human can be 100% accurate in picking which features are going to be most descriptive. Otherwise, this wouldn't be a field. We can't say that we've chosen features that are not irrelevant and therefore bias our estimates in a negative way. Imagine color of a flower wasn't relevant because you have a flower that's like comes in multiple colors anyway, and you're only looking at color as well as stem and sepal length. Potentially including color just biased it towards one of the flowers that only comes in one of those colors. And then there's another flower that comes in that same color and another color, right? Sensitive to scale of the data, which hammers on what we just said, and not competitive generally with some supervised learning models, which are the ones that we plotted at the beginning. Basically, the other models that we can use may be better than KNearest. So a hefty list of drawbacks, to be frank. KNearest Neighbors is kind of, it's a little bit academic in the way that it's like an introduction to machine learning, because it's accessible and quick and fast. But when you use it in practice, you usually ensemble it with another model. So let's talk about some of, or let's implement this in our data. So if you go to the repo, I posted this code. It's good. Okay, so we're going to be working with iris data that is classifying flowers. So the first thing I'm going to do, of course, is read in our data. And if you want to look at the data, it's right here. Looks like this. So it's features that are about the sepal length, width, etc., and then that flower, what flower that was, is what this data is. So this is like the botanist who sent out a bunch of his research assistants, said collect a bunch of flowers and tell me what the petal length, sepal width is, and that's our training set. And we have 150 of those observations. So if we check it out, we got sepal length, sepal width, petal width, and then the species. So in this case, what is our output? It's easy. That's a question as easy as you think. What are we after? Was that? Yeah. Yeah. So we're going to be determining the species of out of sample points based on these flowers that we've already measured. Okay. And this is a good point to introduce the idea that with KNearest Neighbors, all of your data needs to be numeric. Needs to be. Because you're calculating the distances from one point to another point. So often what we'll do to turn non-numeric data into numeric data is anything from like dummy variables to encoding. For colors, you may do the 6-digit color code. For locations, you may do the latitude, longitude, and so on. But significant thing is, like most modeling tactics, we depend on fully numeric data. So here's me importing our plotting stuff and increasing the size of the plotting stuff. And then here's me, I'm going to make a different color map. And this color map is going to be very explicit in the differences between each of those colors. So I'm going to name a color map. My color map is going to be called cmap_bold. And the colors I'm going to tell it to use are, so this is the RGB scale. So full red, 0 is the other, green, blue. All that is. I'm making a color map I'm going to use. Next, what did I just say? We can only work with numeric data. What is our species column? It's a string. So I go ahead and I map each of my species types to a value. Harmless. Okay, now I'm just going to look at my data real fast. I'm going to scatter plot petal length versus petal width in color using my color map that I just created by species. So it's actually pretty neat, right? Like when you plot these two features at the very least. But remember, KNearest plots in multiple dimensions. You can think about KNearest like doing a scatter plot, but in multiple dimensions, where the number of dimensions is the number of features you're using. And then wherever our out of sample point falls in that dimension is where we're going to classify it. Have you guys ever seen Flatland? Yeah? Okay. Yeah. Yeah. There's like a good movie about it, but basically it's the idea of like imagining future dimensions. So it's the same thing here.
So you can only plot it in 2 dimensions, but it can take in way more.
Exactly.
Okay.
Exactly. I mean, we can only plot in 2 dimensions because we as humans suck, but computers don't.
Okay.
I'm just going to plot sepal length versus sepal width, just to kind of see what that looks like. And this one is a lot less precise. It's not nearly as well segmented. You have some of these guys, and some of these guys' territory, and it's a bit more murky. So if we were to combine those two, or combine all those features rather, those two scatter plots, we maybe would be able to have a pretty good estimator, a classifier. So I'm going to do that using scikit-learn. And here, you guys have already used scikit-learn quite a bit, right? Like, I mean, you've talked about the value of it. It's great because there's a lot of documentation. It's consistent with the developers community. It's bad because sometimes it's a bit harder than R to interpret results. Quick little FYI. Okay. So what do we need to do for any modeling tactic? What the first things we need to do? Something about target. Something about divide up into features and what we're trying to say those features mean. So that's what we're going to do here. I'm going to name. This is a quick tactic that I think I've shown some of you in office hours that makes the code you write for one model very scalable for code you write for another model, where you name a list called feature calls, and then that list of feature calls is the one you change from time to time whenever you're working with a different data set. But nonetheless, that means every additional time that you work with that modeling tactic, you can just say your X is data frame and feature calls. So that's a nifty little thing. So I'm going to do that. My X feature calls. And what are the feature columns I'm using? Yep. Then the Y is just going to be the species number. Let's see. Why is it species number? This side of the room, not this side. Second row. I don't know your name, unfortunately.
Adam.
Adam?
Yeah.
Why is Y species number?
I'm not sure.
Okay. Because you can't have a string. Why?
It needs numbers.
Yeah, yeah. It needs numbers to crunch. So we can't work with non-numeric data. To check that, I'm going to print the types. Do you see why?
Yeah.
Yeah.
I
Cool.
was just like a couple lines behind.
Oh, okay, okay. Good deal. And then we do the same for Y. Make sure our Y's check out. And indeed, yeah, some series and some arrays, array of values for the inputs, for the outputs.
You did type X and then type X values.
Yeah, so X itself is a data structure that's holding all of the values within it. So X itself is just a series. The values of the things in that series, in that data structure, is what the values is X.values. So a series is a data structure that can contain values of some type. The values that are contained in my data structure is an array. And so we also need to make sure, like almost every modeling tactic, is that our shape of the inputs and the shape of the outputs match up, because think about it, if there was only 10 outputs and there's 100 inputs, it's not going to know where to map or where to determine to train those 90 that don't have an output against. So let's check that. 150 and 4, 150 and nothing. Is this going to work? They're not the same. Why is that going to work?
Because you have one output, so you're only predicting one thing, which is species.
Yeah, yeah.
You're using 4 different things to predict that.
Right. So taking a step back a sec, this first one is the rows, and this is the columns, of course. So we have 150 rows and 4 columns, where our columns are our features. The output is 150 rows, so great. Each of our inputs are going to match an output, and there's no columns because it's just the outputs. Okay, now the magic, so to speak. We're going to import our KNearest Neighbors classifier from scikit-learn. We're going to name, or rather, we're going to instantiate an estimator. So that's just a fancy way of saying start up a classifier. So KNN is going to be equal to a classifier where the neighbors is equal to 1. And I declared that. So what do you think what is the type of my variable called KNN? It's kind of a neat question. Yeah, I mean, it's, and not only that, but it's a KNearest classifier. It's based on the scikit-learn library. Yeah.
I don't follow the line right above type KNN, where you said it's I don't know what's
This guy?
Yeah.
Okay, so we are instantiating an estimator, which means we're going to make some variable called KNN, where that variable is equal to starting up or making our classifier actionable. So whenever I refer to this variable, I'm going to be referring to starting an instance of KNearest classifiers, or KNearest classifier. And scikit-learn documentation requires when you start up an instance of this, you need to pass it a number of neighbors, a K value. So I passed it 1. So now, whenever I refer to this variable, it is an instance of KNearest Neighbors. Just like you guys have been doing the same when you say model equals linear regression, blah, blah, blah. You're instantiating an instance of linear regression. Or maybe you've been doing LM. Nonetheless, instantiating an instance of a model. So there you go. That's our classifier. Okay, now, what do you think this line is doing? KNN.fit x, y. I think you guys know. I've just been mean today, so no one wants to talk. Yeah. Yeah, it's training the model. Can you walk through each of these, what's going on? So this.
That is the model, which is the KNearest Neighbors.
KNearest Neighbors model.
Yep.
With K set to 1.
Yep.
Neighbors set to 1.
Mhm.
And it is fitting
Yep.
the data that we're getting at, which is the X values, which is the 150 by 4
Yep.
data frame, and the Y values, which is our target
Yeah. Exactly.
species.
Exactly right. Fit comes from the documentation, which is just how you train a model, is you fit it. Okay, so now we have fit our model, which is super great. How do we use it? Yeah, we predict. And so what is this? What is this? Don't run this yet. Don't run this yet. Some people said, oops, and spoiled it. This is going to, I'm just going to tell you too. This is going to output a single value where that single value is equal to what? Species, which is bound by, remember when we did species num? What do we do for species num? What are the values of species num? Yeah, we map them to values between 0, 1, and 2, or values at 0, 1, and 2. Exactly. So the output here is going to necessarily be one of our Y values, one of our outputs, one of our targets, where that target has already been mapped to be 0, 1, or 2. It's going to, and the reason that it takes, why does it take 4 values? There's 4 features. We're passing it. We're saying, hey, I found this flower out in the field, and it has a, I don't remember the exact order of these. It has a sepal length for, sepal width, petal length, and so on, of these values. Oh, I didn't fit. So in outputs, it says 2. What does that mean? It's number 2, which we map to be, do I remember? I don't. We mapped 2 to be Virginica. I know nothing about flowers. So I'm going to make something called x new, where x new is equal to 2 arrays, and those arrays have 4 values each. And then I'm going to predict x new. What am I going to get as an output? What's the shape of my output? Yeah. So you said it. You said it. Yeah, 2 values. And why do you know it's going to be 2 values? Yeah, you're passing it 2 arrays, where each of those arrays contains sepal lengths, widths, petals, etc. So I just made a variable called KNew. You can imagine KNew being a flower that you just picked in the field, or a bunch of flowers that you picked in the field. In this case, we picked 2 flowers, and we stored them in an array called KNew. So now I'm going to say, yo, model, what are these 2 flowers? And it says, well, the first one is 2, Virginica, and the second one is 1, which is the versicolor. Awesome. So we just did KNearest Neighbors. Yeah, we just did some classification. Now we can tune it a bit too. So the way that we tune it is by what? What do we do to tune KNearest Neighbors models? Change K. And the way we change K is we pass it a different value for the number of neighbors. So that's what I've done. And now I can predict, before I run that line, I'm going to do I'm going to do this. Predict that one. I'm not going to refit it. Just kidding. I'm just going to go back to this. So I'm going to do predict proba x new. When I do predict proba, what I'm doing is I'm asking for the probabilities that those those number of values that I passed. So in this case, x new is 2 different flowers, right? So I'm going to ask for the probability that each of those flowers falls into my target outputs. Yeah.
So when you change the number, okay, you don't have to refit that model to the same model. We're changing the
You have to refit it.
Okay. So we need to.
Yeah, here. Sorry, I'll move that. I'll move that down and then correct that in the repo as well. And the reason you have to refit it is because right now our model is fit for a value of 1, and so it's gonna continue to do that accordingly. So we need to refit our data where the value is 5. And so when we do predict proba, as I said, we get the probabilities for each of those inputs being each of our outputs. So we get 2 arrays where each array corresponds to one of the inputs, and each value in that array corresponds to the probability bounded by 0 to 1 that this input is indeed the corresponding output. So our outputs are 0, 1, and 2. So here's the probability that the first flower is type 0. 0. The probability that's type 2 is 0.8. The probability that's type 3 is 0.2. So the equivalent way to think about this is the shades. The shades of our visualized K-nearest neighbors model, where this shade is going to be mostly the color 2, but with a little bit of a gradient. The next one, it gets values of 0, absolutely 0% chance that our model thinks that this inputted flower is of the first type. It gets a 100% chance, 1, that it's of the second type, the versicolor, and a 0% chance that it's of the third type, which was the virginica. So if we visualize this one, we would see that it is the full shade of the second type. And now you'll see, going forward, we've discussed bias variance trade-off, and we've discussed K-nearest neighbors, but we haven't really discussed how those two overlap to apply the bias variance trade-off to finding an ideal value, in this case K, for our K-nearest neighbors classifier. So you can kind of see where we're headed. But now the tools you've been equipped is understanding the trade-offs that you make in a model when you increase its complexity, and you've understood the type of model, linear regression, the type of model, K-nearest neighbors. And then in the future, we can merge those things and find ideal values that minimize our error. But yeah, that's it for today, is K-nearest neighbors, how to implement it, what it is, what classification it is. Bam. Other questions? Something I want to footnote in this discussion is K-nearest neighbors is sensitive to the scale of our data. As in, think about it, it's calculating distance from one point to another point. And let's imagine that our feature columns, like petal length, stem, etc. Let's just, for the sake of example, pretend like sepal width is always going to be like 0 to 10. Sepal length, 0 to 10. And then stem, like just the full stem, is like 1,000. Between 1,000 and 10,000 even. When we train a K-nearest neighbors model is trying to minimize the distance between new points to each of those old points. So if it's minimizing distance, do you see a problem that could arise from a model that's built on data that is of different scale? The model is going to try to minimize distances, and if those distances are non-equal in our training data, it's going to try to minimize the distance of the huge value. Therefore, our K-nearest neighbors classifier is going to be biased by that one value that is extortionately large compared to the others. And there lies feature scaling, right? Or regularization. But that's something to be conscious of when you're working with the K-nearest neighbors classifier, is in calculating distances from one point to another, you're inherently caring about those distances. And if distance for some points are non-equal between other points, and on entirely different scales, that different scale is going to, in effect, get more weight. So I guess I asked myself a question and then answered it. Do you guys have questions? Yeah. Yeah.
So I heard different features as variables.
Yeah.
Is the word feature synonymous with like input variable? Because reading a little bit online, they made a distinction between linear regression. You've got your target, you've got your predictor variables. And then you have your features, which are the degrees of your polynomial. Is there?
So features being used in two different ways in that context. Features being used to describe the features of your model and the features of your data. So the features of your data is the variables. The features of your model are the degree, et cetera, which means what you're reading online was probably like, be careful when talking about features because there can be ambiguity in if you're talking about the model features or the features of your data. But there's no wrong, so to speak. Yeah.
The last line there, when it predicts the execute,
Mm-hmm.
so we change the end.
Mm-hmm.
For the second flower, it predicted a 100%
Mm-hmm.
chance that it's the second.
The versicolor? Yep.
Yeah. Is that the model saying, okay, you trained me to do this, I'm 100% sure this is the right classification? Is it possible that the model is wrong though, out like in the real world? See what I'm saying?
Absolutely. Absolutely.
Okay.
And
so the model, according to itself, is 100% correct in its guess, but it could be wrong.
absolutely.
Oh, it's not. Okay.
And therein you're finding the value of building an estimate or accurate models. A model is only as good as the data scientist who has built it. So if your model says 100% and the model did the best it could for that value, that doesn't necessarily mean it's accurate. So that's why we rely on toning down error and stuff. But I mean, let's say, if you built a very nice model and you got a 100% chance of something, perhaps you should be pretty elated about that, and trusting even. But I mean, the parallel here would be like, imagine grabbing one of the points in this giant blue cluster, bottom center. Like imagine grabbing the center one there. If a model says 100% about that, you probably built a pretty good model, potentially. I mean, it would matter more about what it's saying about ones in the marginals. But nonetheless, a 1 should not be cause for, oh shit, this is a bad model. It could be a very good model, and you're just in the thick of the woods. Odd values of k is better than even values, generally, because you're breaking ties. Yeah, I mean, that's We're over time, but I can answer questions before I have to jet off in like 5 minutes. Cool.